Welcome to the lecture series on mathematical modeling, analysis and applications. In the last lectures, we have discussed about linear discrete models based on first order and second order differential equations. And also we have discussed the system of linear differential equations. So, in this lecture, we will just discuss about this numerical methods to compute the eigenvalues. Since eigenvalues is important in aspects of checking the stability. So, if you will just go for this eigenvalue computation. So, first we have to understand what is the physical significance of eigenvalues. Then why numerical methods has been used for this calculation of eigenvalues, is it necessary? So, thirdly we will just go for like different numerical methods to compute the eigenvalues, and then we will just discuss here only two methods, that is like power method and LR method for the computation of eigenvalues. So, if you will just go for this physical significance of eigenvalues that we have just discussed in our previous lectures, that the eigenvalues will be used for this calculation of the stability condition, or the characteristic equations can be derived from the system of equations in terms of matrix notations. And then if the eigenvalues are calculated, then it is just showing whether the system is stable or unstable. By the time you might not have completely realized the things, since we do not know exactly the importance of eigenvalues in finding the stability of solution exactly, and hence analyzing behavior of this eigenvalues is important to understand or realize the importance of the physical behavior inside the system. So, do these eigenvalues describe something, or are they mere same just representing some numbers? So, eigenvalues and eigenvectors, where we are just saying that if eigenvalues are existing for a system of equations, then corresponding to each eigenvalues we will have certain eigenvectors, maybe it is repeated or maybe it is like distinct. So, they are very well related with each other for a transformation of any system. The need of transformation of system is to make it easier for study and analysis. When you transform any matrix, you need two things, at best I can just say. By what amount are you going to transform your system, and in which direction you are transforming. So, if you will just consider here these 2 points, then we can just study the behavior of the system which is represented in the form of a matrix. If you will just go for like little depth in physical sense of eigenvalues, you can just find that the first question will arise that the eigenvalues is given, or if it is given, how it is associated with the eigenvectors. Suppose if you have a 2 by 2 matrix and its eigenvalues are suppose lambda 1 and lambda 2, and corresponding eigenvectors you are just representing as V1 and V2 there. Since especially whenever we are just writing this eigenvalues, so especially it can be represented in terms of a vector, suppose V equals to lambda 1 V1 plus lambda 2 V2, which is expressed as a linear combination of V1 and V2 also we can just say. So, if you will just go for like this transformation of the system, so if we will have like two distinct eigenvalues, suppose lambda 1 and lambda 2. So, lambda 1 gives the amount by which one is transforming matrix in direction V1, since V1 is the associated eigenvector with this eigenvalue lambda 1. Similarly, in case 2 with lambda 2 in direction of V2. Since especially we can just say that these eigenvalues, they are just transforming the systems in such a way that it just takes a direction which is the associated vector direction. And if suppose the eigenvalues value is lying between 0 and 1, the system is contracted in the direction of V, since it is already a bounded system there. If lambda greater than 1, this means we are just going far from 1 there, means the system is expanded in the direction of V. And if suppose lambda greater than minus 1 and it is less than 0, then the system is contracted in the opposite direction, since if you will just define the axis here, and we will have like the values are existing, suppose 1 here, then 0 here, then minus 1 here. So, we are just assuming when this lambda is lying between here and when this lambda is lying between here, or when we are just considering lambda lying between here and also lambda lying between here also. So, these 4 situations or the conditions we are just assuming to study the behavior of the system, whether it is just transforming towards the direction of V1 or V2, or if we are just combining this system, then whether it is just behaving towards V or not. So, if we are just seeing here lambda is less than -1, suppose the system is expanded in the opposite direction of V, and if lambda equals to 0 means the system is not at all transformed in any direction of V. So, if we will just go for this numerical methods, since as we have discussed in the earlier lecture that always we will not have a like analytical solution, since this analytical solutions can be possible whenever we will have like a quadratic equation, and after that it is not easy to find the values when this degree of the equations are greater than 2. And any mathematical problem associated with this physical significance, it is important in the aspects of eigenvalues, and each of these eigenvalues are associated to the eigenvectors, and also we have seen that how tedious job is to calculate the eigenvalues when matrix is of higher dimensions. Also, when degree of a characteristic equation is large, that is more than or equal to 3, it is not even easy to find the eigenvalues. So, already we have discussed the Jury's test in the earlier lectures, that it can just help us to know whether all the eigenvalues lie in a unit disk or not. But to know the exact solution, we need the eigenvalues. When finding the solution of a system or an equation becomes a difficult task with analytical methods, then we are just going for the numerical methods. So, numerical methods will provide you an approximate solution, not the exact solution, since this is associated with a certain order of negligence there. So, usually numerical methods are the computer based approaches which try to converge near the exact solution as far as possible, since we are just neglecting here higher order terms by considering some aspect ratios. So, first if you will just go for like numerical methods for the computation of eigenvalues, there are many numerical algorithms to solve or to compute the eigenvalues. Some of the widely used algorithms for finding the eigenvalues are like power method, LR method, QR method, and householder methods. But each method has also certain like discrepancies or like drawbacks are there. And in this lecture we will just go for like a power method and LR method, which is used to find the eigenvalues, and the first method, power method, is used for this like largest eigenvalue for a matrix A, or we can just say the smallest value of matrix A inverse, and LR method which can be used to any arbitrary matrix to find all the eigenvalues. So, in the power method especially, the method is based on like a computer oriented method that finds the largest numerically dominated eigenvalue. Sometimes in this method also we are just shifting the points towards the origin or towards the like desired point there. So, that is especially called shift of origin points, and we are just shifting these points to find the largest eigenvalue close to that points. In order to find this subdominant, say second largest eigenvalue, the size of the matrix can be reduced by 1 and power method can be applied on newly formed matrix. And power method is an iterative method, especially it is also a costly method, and we need the initial assumptions to start the process, and after each iteration we will compare the solution obtained with the previous iteration solution for the convergence criteria, and if after certain iterations difference between two successive iterations achieves this degree of accuracy, then we can stop these iterations, and that solution is said to be a converged solution. This certain quantity relates the accuracy of method for a particular matrix. So, for example, if you just go for a power method, then we can just find the largest eigenvalue of any system of equations by considering the initial approximation. If the initial approximation has not been given to us, then we can just assume as 1 1 1 or 1 0 0 or 0 1 0 or 0 0 1 there as the initial guess vectors. So, especially why it is called the method to find the largest eigenvector is that we have to assume that the eigenvalues are placed in the form like lambda 1 should be larger than lambda 2 should be larger than lambda 3. So, like that way we will have to consider here. Since whenever we will just find this eigenvalues, so if we are just writing in a like a determinant form, that is determinant of a minus lambda I equals to 0 here, then if A is a like n by n matrix, this will just represent a polynomial of degree n here. And if we are just considering the lambda 1, lambda 2 up to lambda n are arranged in this form and each lambda i's are distinct, then this will produce like the eigenvectors are linearly independent, or if the eigenvalues are distinct, we will have like n number of linearly independent eigenvectors will assist with this distinct eigenvalues here. And if we can just find that any vector which can be expressed as a linear combination of like lambda 1 v 1 plus up to lambda n v n here, since lambda 1 is the largest element we have just considered here, and we can just consider lambda 1 common here, or if you will just pre-multiply this matrix A for this V element here, we can just write it as lambda 1 A V 1 plus lambda 2 A V 2 up to lambda n A V n here. And obviously, we know that A V 1 that is nothing but lambda 1 V 1 again, then lambda 1 plus lambda 2, and again you will have like B 2 lambda 2. So, likewise we can just write also. So, in the first matrix, if you just take common suppose lambda 1 here, we can just write V 1 plus lambda 2 by lambda 1 V 2 up to lambda n by lambda 1 V n. And if you just see here lambda 2 by lambda 1, it is like less than 1 here, and if you just see lambda n by lambda 1, it is also less than 1 here. And consecutively, if you just multiply this matrix suppose n times, we will have like here a to the power n v. This will just give you like lambda 1 to the power n here, then you will have a v 1 plus lambda 2 by lambda 1 whole power n v 2 plus remaining elements. When n tends to infinity, then lambda 2 by lambda 1, it is a very small quantity, and all other quantities it can be just neglected, and we are just remaining here with a lambda 1 to the power n. And if you just take like a n plus 1 v here, this will just give you lambda 1 to the power n plus 1, and remaining factors it will be just there. And if you just compare these coefficients, we can just find that lambda 1 is the largest eigenvalue for this matrix here. And based on these approaches, we are just assuming that at each level we are just taking the largest element common here. So, that is why we are just writing this matrix in the form like A x 0 as like 2 minus 1 0 minus 2 minus 1 0 minus 1 2 and 1 0 0 here. If you will just multiply, then we can just find this is a 2 minus 1 0 here. If you will just take common the largest, whatever we have just done for this system here also, the same thing you will just do here, that is 2. If you will just take common, it can be written as 1 minus 0.5 0, which can be written as lambda 1 x 1 here. And if we will just multiply this x 1 vector again with this matrix A here, then we can just find this is the complete vector here. And from that, if you will just take largest magnitude of the vector, so it can be just taken common as 2.5 here, then the remaining elements are like 1 minus 0.5 and 0.2 here, which can be written as lambda 2 x 2 here. And this process will continue, and finally, we can just obtain A x 3 as 3.43, 0.87 minus 1, 0.54, which can be written as like lambda 4 x to the power 4 here. Again, we have to multiply A 4 x 4 with the matrix A, which will just give you 3.41, 0.80 minus 1, 0.61, which also can be written as lambda to the power 5 x to the power 5. Again, we will just take x 5 here and multiply with this matrix A. Then we can just find as lambda 6 x 6 here. But the difference, if you will just see here, that is with this eigenvectors, that is 0.76 minus 0.80 and then minus 1, 0.65, 0.61. So, whatever this accuracy we want to find, based on that we can just find that one. Accuracy means we can just say that xi k plus 1 minus xi k, it should be less or equal to your desired accuracy, that is a half into beta to the power minus t here. Beta is the base and t is the number of digits or decimal places you want to find the accuracy here. And to find the smallest eigenvalue, one can use the power method, that is if you will just find A inverse the largest eigenvalue. So, that is the smallest eigenvalue of A inverse there, or we can just say that for smallest eigenvalue of A inverse is 1 by lambda here. So, then we will just go for LR method here. The LR method was first suggested by a Swiss mathematician H. Rothishauser in 1958, and this method can be used for any arbitrary matrix to compute all the eigenvalues, and this method generally takes two steps. In the first step we can just write AK equals to LK RK, and second step we can just write AK plus 1, this is RK LK. If like L and R both are symmetric matrices, then both these values are equal there, where k equals to 1, 2, 3, obviously we can just take, and first we can just consider A1 equals to A here, and we are just taking here LK is the unit lower triangular matrix, while RK is the upper triangular matrix. And for large K matrix AK plus 1 generally approaches to an upper triangular matrix, that is the determinant of an upper or a lower triangular matrix is simply the product of its diagonal entries only. So, the eigenvalues are given by the diagonal elements. Obviously, sometimes if you are just finding only the diagonal entries are there, that is nothing but the eigenvalues of these matrices. So, if you will just consider one example on LR method. So, suppose the example is written like find the eigenvalues of a matrix A, which has given as A equals to 3, 2 and 1, 4. So, first we have to assume that A1 equals to A, which can be written as L1 R1 here. So, L1 is nothing but the lower triangular entries and R1 is the upper triangular entries. But in this case we are just assuming this problem will be solved by Doolittle's method, and in the Doolittle's method we can just assume to this lower triangular diagonal entries as 1. If we will just use Crowd's method, then we can use this U diagonal entries as 1 there. But since we are just taking as the left product of this elements here, it is better to go for this Doolittle's method. As you know that to equate this number of variables with the number of unknowns, especially we are just reducing or we are just considering this diagonal entries as 1 here, since neither we will have like 2n plus 2 unknowns if you will not consider this diagonal entries of any one of L1 or R1 is 1 there. So, from first iteration if we will just compare all the coefficients, that is the product of L1 and R1 with this matrix A here. So, obviously we can just write here 1 0 alpha 1 1 and product of like alpha 2 alpha 3 0 alpha 4, this equals to obviously you can just write as the 3 2 1 4 here. And we can just take this product like alpha 2, this is nothing but 3 here, and then we will just take the product of this one. So, you will have alpha 3 equals to 2. If you will just a product of this one alpha 1 into alpha 2, this is nothing but we are just going the product in this form. So, that is why we will have like 1 here. So, obviously alpha 2 it is known as 3 here. So, that is why alpha 1 equals to 1 by 3. Similarly, if you will just take a product of these two here, so we will have like alpha 1, alpha 3 plus alpha 4, this is nothing but 4 here. And if you will just calculate alpha 4 by putting alpha 1 and alpha 3, we will have this value is 10 by 3. Now, if you will just go for the calculation of A2 here, so A2 can be written as R1 and L1. So, if you will just take the product simply you can just get this is the matrix here. So, similarly we will just go for the calculation of again L2 and R2 by the same method, and this process will be repeated until we get the same matrix A in the successive iterations. So, in this case after performing 10 iterations we are just getting A9 as 4.9952, 2 and 0, 2.0023 and A10 as 4.9976, especially if you just see here the degree of accuracy is coming up to third decimal places, and 2 is exactly 2 here, and 0 is coming as 0.0024 and this is also coming exactly same. So, you can observe that A9 and A10 are almost identical and diagonal along the diagonal entries. Hence, the eigenvalues are obviously we can just consider as the next immediate approximate values as 5 and 2 here. So, this exact eigenvalues can also be verified using Jury's test that you can just make it. So, in this lecture we have discussed the physical significance of eigenvalues, then need of the numerical methods, why we are just going for the numerical methods, then numerical methods for computing eigenvalues, and then we have discussed about power methods, and based on one example, then we have discussed about LR method. So, now we will just come for this summary of these lectures whatever we have just discussed in this week. So, if you just see here in the first lectures we have discussed about what is mathematical methods or what is mathematical models. So, mathematical model is nothing but the abstract model that uses these mathematical languages that we have just discussed, and these mathematical models based on deterministic and stochastic models we have considered, and again we have just defined these mathematical models, that is in the two forms. It is represented based on time systems. So, first it is called discrete time system that we have discussed in the previous lectures, and then again we will just go for continuous time system, which will include ODEs and PDEs, that is ordinary differential equations and partial differential equations, and this discrete time system that involves difference equations. So, in the difference systems or the difference equations in discrete time levels, we have considered linear models. So, in the linear models we have just considered a first order difference equation for linear cell division model, and a system of two first order linear difference equations for prey-predator model, and that is for non-edge structured models we have just considered. And last lecture we have discussed about edge structured models, and in the edge structured models we have considered this Fibonacci rebate model. In the last few lectures we have discussed that one, that is second order difference equation, and then we have just discussed the human population level based on this edge structured models, which involves 5 first order difference equation and which is represented in the form of Leslie's matrix, and then we will just go for nonlinear models, and basically the methods used for the solution of linear discrete models are analytical solution we have discussed already, then homogeneous difference equations and non-homogeneous difference equations, that is especially when this migration is coming to the picture that we have just discussed. Then graphical solution methods also we have discussed based on this co-wave graphs valid only for first order difference equations. Then we discussed about how we can just find this equilibrium points or steady state conditions, and especially this equilibrium points occurs when we are just considering xn plus 1 this equals to 0. Also sometimes it is known as critical points. Then we have discussed about the stability analysis based on this eigenvalues. So, sometimes it depends on this parameter for single equation, depends on eigenvalues for system of equations, and we have also discussed the Jury's condition, which is used for higher order equations or determine whether all the eigenvalues are within the unit disk or not. Then finally, we have discussed the calculation of eigenvalues based on numerical methods. Two different methods we have discussed completely by considering certain examples. So, first is power method and second is LR method. Thank you for listening this lecture.